Okay, so I'm going to switch to a different topic from dwarf galaxies that have dominated the last few talks. I'm going to present mostly work in progress on a new simulation project where the goal is pretty ambitious, is to be able to understand using the same simulation or combination of simulations the formation of big galaxies and the physics of galactic nuclei. And most of the work is being done by students in Zurich, in particular Valentina and Davide, but also some of the other people who are here, like Robert and Javiera. So, by the way, we call this project Argo, just continuing on the theme from Greek mythology that started with Ares. We were sort of coming from there. That's the legacy. As you know, Argo is the ship of the Argonauts, which brought together the best heroes of ancient Greek in order to set up on a mission for the Golden Fleece. So you need the best heroes in order to find the most difficult things. And I don't know whether we will find the Golden Fleece, but we will try. So the legacy behind the project is, again, at the same time looking at the formation of big galaxies and going down to very small scales. And for small scales, they really mean going down to subparsec scales. For the first objective, formation of massive galaxies, where we come from is this is Ares and the dwarfs. And Javiera has talked about Ares during the week, I know. And today you have heard about dwarf galaxy formation from Piero done with gasoline. And so we think that we made some progress in showing that with a certain set of recipes and a sufficiently high resolution, we can simulate reasonably well the formation of a spiral galaxy, and at the same time also with the same kind of recipe simulate the formation of dwarf galaxies like you see here. These are the ones that, one of those that Piero discussed in his talk. And the recipe is essentially very high resolution, at least 10 to the 4 solar masses in your mass resolution in the hydro force, in the hydro component, which is also the inspiration behind the Agora project, and a feedback model that combined with a high star formation density threshold allows you to model the cluster mode of star formation and have energy dumped in localized regions rather uniformly in the galaxy. We've seen that there are many other recipes that people are working on that can apparently also be successful. And so it's unclear at the moment what is actually the more physical model. But for me, the question now is, with the same kind of recipe that was able to reproduce in a reasonable way most of the properties of spiral galaxies and dwarf galaxies, can we also match the properties of bigger galaxies, early types, ellipticals or zeros? And can we do it also in dense environments? These simulations, like many of the zoom-ins, are usually based on taking a volume that is in a fairly isolated region, a low-density region, and you follow just one galaxy at a time in most cases. So is this applicable to a more general galaxy formation model? And again, the other component is nuclear scale physics, understanding the formation and the growth of supermassive black holes. We know that there's a huge range of scales that we need to resolve in order to tackle the problem, from cosmological scales down to the scale of galactic nuclei. Of course, no one will be able to really do that for a long time. But I think that it's crucial to at least get down to a resolution where you can resolve the circumnuclear region of galaxies, so a region of about a few tens of parsecs. In order to resolve the dynamics of the gas within a few tens of parsecs, you need to go down to a resolution of parsecs or less. And there have been some works that have tried to do that. For example, all the interesting papers published by Elliot Quartet and Phil Hopkins, but they always looked at non-cosmological initial conditions. So they focused on a set of simulations at different resolution, but starting from equilibrium galaxy models or mergers, but not cosmological. And we are trying now to do it starting from cosmological initial conditions. So here you see one of the simulations, that's the first simulation that is part of this Argo project, is the formation of a galaxy group that by redshift 0 will be 10 to the 13 solar mass halo, which we hope should form a massive central galaxy with a morphology typical of an early type. So the higher resolution region is extremely large, essentially is almost 8 times bigger than the high resolution region in a simulation like Ares, and the resolution is the same as Ares. So we are trying to follow with the same resolution of Harris an entire population of galaxies that lives and evolves in this group. And so that's what we really do different from what has been done before. I think I call it a large zoom-in. It's a zoom-in simulation, but with a very large volume. The largest, I think, that has been tried so far. And then what we do in addition to that, at selected redshifts where we see something interesting happening, like a merger or a strong mass accretion due to a cold flow that leads to a fast accretion rate, we apply particle splitting to increase the resolution and look at the nuclear physics with, in this case, a resolution that goes down to 0.1 parsecs and 2,000 solar masses. Here is an example of two objects that we pick, M4, M3. There are two mergers happening at redshift 4.5. And they are continued with particle splitting, so we select a smaller region, but still large enough, several tens of kiloparsecs, that can actually, co-moving, so a few kiloparsecs at this, in physical at this redshift, still large enough that we can really follow the gas dynamics from large scales to small scales and see how the inflows of gas in the central region happen during the mergers. Now, so the two benefits that we hope to get is really the fact that we should have a population of galaxies rather just one, done at the same resolution that we use for Eris. And also, in a sense, you can think of this Argo project as a simulation that can spawn many others, because we are running several particle splitting runs, selecting different objects with different properties, different merging conditions, and different locations in the filaments where the group of galaxies is assembling. Now, I just mentioned before about the goals. The formation of massive elliptical galaxies is one of the ideas. And I want to stress that we are not going to include any AGN feedback in this work. And I want to stress it in particular now, because I encourage people to look at the talks of last week at the KTP Black Hole Conference, of which I'm one of the coordinators. And one of the interesting highlights there, which for most of you is probably not news, is that there is a really weak evidence of an effect of AGN feedback on global galactic scales. There's an interesting set of results from the MPE group, the Buongiorno et al. Paper, which combines the Cosmos data and XMM data, which really make the point that there seems to be essentially no effect when you look at stellar mass or star formation rates between galaxies that have an AGN and galaxies that do not have an AGN. And so this is sort of telling us, I think, that if we want to try model massive galaxies, first we have to see what we can do without including AGN feedback at all. And so that's one point that I would like to stress. And the other point is that nuclear gas physics is not only important to feed a central black hole or feed a nuclear star cluster, but in some models for the formation of the black holes themselves, the central massive black holes themselves, it might actually be important to trigger the formation of a seed black hole. There's different models around to form seed black holes by direct gas collapse rather than by a slow growth from a POP3 seed. We have worked on one of these models in the past, which we published in this paper here, and then we worked on an extension of the model using semi-analytical work, and we want to see whether we can actually verify the model in a cosmological setting. And then star clusters will be also another highlight. Now, some examples of what we get at the moment. So the simulation is a redshift about 3, and these are snapshots taken at redshift 3.7 for some of the galaxies. This is the most massive object that is accumulating most of the gas at the convergence of more than one cold filament. And these are some of the other more massive galaxies. So in the second, the third, and fourth, and fifth, and sixth most massive relative to the primary galaxy. As you see, all of them show spiral structure and flocculent harms in some cases. We are starting to look at the kinematics. All of them show disk-like kinematics. So all of them have a disk. This is not news. We know that any galaxy starts from a disk. We are looking at structural properties in quite some detail. This is a compilation of the rotation curves of the galaxies at redshift 4 in the group. As you can see, there are all sorts of shapes, from quite steep rotation curves to extremely flat rotation curves. And the question is how you get different shapes. And we are looking now into reasons behind that. This is an example of the interesting hints that are coming up that when you look at the concentration of the rotation curve, so the ratio between the maximum circular velocity and the virial circular velocity. And you say, okay, let's not get into problems with resolution. Let's only look at the very high end of the mass where the resolution is extremely high, because at this high end, already at this redshift, we have several hundred thousand SPH particles per galaxy. And the most massive is already 1 million about. And you can see that there's a large spread in this concentration parameter at the same mass. So even at the same mass, you have a wide variety of structural properties. The fact that they tend to converge to a flatter curve here, I think is just because we're getting to resolution effects. You're not resolving the peak of the rotation curve well enough. But we are going to look at why you get this spread of structural properties even at comparable mass scale. Now, all this stems from previous work that we have done 2-3 years ago with Robert Feldman, who's here in the audience, where we had looked already at this, one of these groups, the one of which I showed the movie, but a much lower resolution. In that case, we brought the simulation to low redshift, and we studied the population of galaxies. At that time, the resolution was 64 times smaller than the resolution that we are using now. It was pretty good for the epoch, but currently it would be a very low resolution simulation. Still, we had about 13 galaxies with a stellar mass close to 10 to the 10 solar masses, which we could study, and these are the ones with the numbers in the plot. And one interesting thing that came up there was that we could form objects that were relatively close in structure to elliptical galaxies or a zero galaxy in the center. They had hot kinematics. This is an example of a slit measurement of the velocities, where you see that the velocity dispersion dominates over the rotation. There was some rotation in 2 of the massive central ellipticals, but not in the third one. But the problem that came up, which was pointed out also by other people, is that when you start measuring structural properties, correlation between structural properties, for example, the correlation between the effective radius and the velocity dispersion, we ended up with galaxies where the central galaxies were all too compact to be representative of the typical elliptical galaxy that you see in the present-day universe. So this is the distribution from this paper for local elliptic, well, low redshift early types. These dots are from compact galaxies at higher redshift, and you see that we are actually fall close to the compact galaxies at higher redshift and not in the typical region where you expect early types today. So the galaxies were too compact for their mass, essentially. Too dense. The effective radius was too small. The velocity dispersion too high because you have too much mass in a small region, which is, again, the same problem that before everybody had seen for these galaxies, the angular momentum problem. Then you look at the evolution of the central density. You could see that it's flat with time. So it means that you build up very high stellar densities from the very beginning, and you're essentially left with that wrong normalization of stellar density down to low redshift. You never solve the problem late. You have to solve it early. So again, this problem was also present in these galaxies and in dwarfs, but then at least with Eris and the dwarfs, there's been progress in showing that this can be solved. So now the question, as I started from the beginning of my talk, is the same recipe applied to this massive galaxy scale does produce improvements or not? So when you go to this 10 to the 4 solar masses resolution and you used I-star formation density threshold, do we see a change compared to this previous result that was sort of discouraging? We do see that, because if you compare a redshift 3.4, where the simulation is now, so that's the analysis done just these past few days, redshift 3.4, you clearly see a difference from the old. Look at just concentrate on the difference between the solid line and this magenta line here. The magenta line is one of the massive central galaxies in the plot that I showed before, where they were in the compact elliptical regime. And this is the same simulation with the new resolution, with the 10 to the 4 solar masses and high density threshold of star formation. And you see there's been a decrease of stellar mass at all radii. So you've gone down by a factor of almost 2 in stellar mass. And the density also here has gone down by a factor of about 6 from here to here. So it's clear that this cluster mode of star formation is doing something even at this mass scale. But of course, the simulation is still at redshift 3. We don't know what will happen next. But that's just to say that the trend is going in the right direction, that we do see a significant difference even at this very large mass scale, as we saw for Eris and for the dwarfs. Now, the other thing which I'm going to discuss just in a couple of minutes is the application to the central physics of galactic, the physics of central galactic regions, the nuclei. As I mentioned, a few years ago, 2 years ago, we published this work where we proposed that you could form a seed of supermassive black holes from a galaxy merges with a relatively high redshift. That was a redshift 7 configuration for the properties of the galaxies taken from a cosmological volume. But the galaxies were actually merged with a binary merger, so they were not in a cosmological setting. But we saw, reaching 0.1 parsec resolution, we saw the formation of a supermassive gas cloud just after the merger, driven by a multiscale inflow of gas that started from kiloparsec scales and continued down to subparsec scales due to a nested series of instabilities, spiral waves triggered at different scales. Now, this massive cloud was 10 to the 8 solar masses, Jeans unstable, and it would have collapsed further if we had a resolution even higher than 0.1 parsecs. Now, we are working on refining the model in different ways, but a first question is, will you see the same thing if you had started from a cosmological initial condition? So can you actually have a model like this working in proper cosmological initial conditions? That would be interesting because it would be a way to form massive black hole seeds that in this case doesn't even require low metallicity gas, because this was actually done for the condition of redshift 7 where the gas is already metal enriched. And so that's what we are doing now. That's an example of one of these simulations, starting from the big Argo zoom-in box where we do particle splitting in a region. So we reach 0.1 parsecs, and we simulate a merger at 0.1 parsec resolution. So this is the merger of the nuclei of the two galaxies. So we start at a point where the outer part of the galaxy has been already stripped. And you see now, really zooming in to smaller and smaller scales, as you can see from the bar here, the merger of the two galactic cores. And you will see that they end up in a circumnuclear rotating disk. This particular model is just illustrative because it's based on an effective equation of state. And that has a pressure floor that doesn't actually allow you to look too much in the center because the medium becomes pressurized. But we are now looking into the more physical models. I'm actually showing here, where we do include everything, star formation, feedback, radiation, and we can really follow the inflow with a more proper physical model down to subparsec scale. So I don't have results, but that's where we are going. We hope to be able to show that we can recover the same properties of the binary mergers and forming a massive Jeans unstable cloud in these realistic cosmological initial conditions. For the current runs that have this equation of state, rather than the proper radiation physics, we do see mass accretion rates that are quite large in the region, in the 100 parsec. They get up to 10 solar masses per year or more. They would be interesting to grow an already existing black hole, but they are not what we need to make the seed, because in this simulation where we could make this big supermassive cloud that could be a precursor of a seed, we reached accretion rate of 10 to the 3 to 10 to the 4 solar masses per year inside a parsec for 10 to the 5 years. So the question is, will we be able to reach that in these proper conditions with this kind of runs? We will see. So stay tuned for future work. Thank you.
Not only just for you.
Yeah.
So I'm not a simulator. When I'm looking at these presentations, what I really would like to see is something like this. Is within my simulation approximations, within my the limitation of my method, this is the set of prediction of my model, and observers can go there and see if it is, the model does not match the observation. That's more.
Mm-hmm.
That's more. So I haven't seen anyone just make such a prediction. And I just don't know how long it will take we reach to that kind of stage. Say we have these predictions, we understand the numerics and everything well, and of course the physics, this is what I assume, and this is my prediction.
There was an example of that, right?
Okay, yeah.
When I showed you, where is it? Here. That we couldn't match with the old simulations, not the new ones that we are doing now that I presented today, but with the old published simulations, we could not match the typical effective radius versus sigma relation of ellipticals, which should be around here, whereas we were here with these 3 dots. That's an example of a prediction of the simulations that was immediately falsified by observations, because we would have predicted that elliptical galaxies should have this kind of properties, whereas they should have this kind of properties, to be typical, to be representative. Okay? So, a redshift 0, we sit where the compact galaxies at redshift 2 are. So that's clearly a comparison with observation that tells you that the model is wrong. That's the motivation of doing the new simulations with more resolution and a different star formation, a higher star formation threshold, as we did for Eris. The hope is to see whether we can resolve this discrepancy.
So this is wrong is because of the numerics, or is it due to the physics you assume is?
I think, there is not a definite answer to this. My opinion is following up on what we claim also in the papers on Eris and on the dwarfs, including the new work that Piero showed, is that it's a combination of resolution and the ability to resolve the cluster mode of star formation. At least that's a way that we think this can be changed, in the sense that if you go to higher resolution, you resolve the inhomogeneity of the ISM, then the star formation becomes more clustered, and the feedback, even if you don't change the feedback, becomes more localized. And that's how we showed in Eris we could produce a disk that was certainly much better than the disks that were produced by previous simulation. So now the question is, can this kind of model, resolution, clumpy ISM, cluster star formation, work and solve the problem also at this very high mass scale? We are talking about galaxies with this velocity dispersion, 200, 300, so massive S0 elliptical galaxies, where the feedback from stars and from supernovae is inherently less effective because the potential well is deeper. But can this have sufficient effect to move you towards the left? That's the question.
Lucio, I can answer your question as you know. Let's change the cooling, add in AJ feedback like that.
I don't know. I mean, I don't believe we know. I think we should use Occam's razor and see what we can do with a model. No, but you see, it's not. This galaxy is 300 kilometers per second at redshift 0. But at redshift 3, it was lower mass than the Milky Way. So the feedback happens over time. It's not just happening at redshift 0 when the galaxy is so large. Of course, at 10 to the 13 solar masses per year, I would have no effect of supernova feedback.
So what is the next prediction that can be used to falsify this model? The high resolution, new method?
Well, you have to look at a combination of properties. I think Javiera probably discussed that in her talk. It's not, you can never say that your model is right with just show. You can say that your model is wrong by showing just one plot. Okay? But if you want to show that a model is correct, you have to put together all the possible observational constraints.
But that's exactly my point.
Yeah, so if we solve this, then we have to look at metallicities, star formation histories, everything essentially. Yeah.
You have time.
Yeah. Okay. What's that?
Aren't your elliptical galaxies rotating too fast? There's a clearly sense of nice rotation in your elliptical galaxies. My recollection is that velocities, the 100 per second elliptical galaxies.
That's a good point. So that's, yeah, well, there are zero galaxies that are as large
But it's
as...
not a zero, right?
No, well, that's a semantics problem. How do you define an elliptical? Now you define as...
Some elliptical galaxies do elliptical galaxies, which don't rotate.
There are ellipticals that don't rotate. In our sample of 3, we had 1 that was not rotating and 2 that were. So it's a sample of only 3 galaxies. I don't think you can... But I agree that it's an important point. The kinematics are an important point.